Last lecture, we solved the sequence-to-sequence bottleneck problem using the cross-attention mechanism, where we built an attention-augmented RNN, where the encoder RNN here processes the source sequence to build a memory bank H1 to HT. The decoder RNN generates the target sequence step by step. For example, here we are looking at the step T of the decoding, where this cross-attention lets the decoder query the encoder memory to compute a dynamic context vector CT. This solved the information bottleneck and improved the quality of translation dramatically. Models could handle longer sequences, and this approach became the state-of-the-art from 2015 to 2017. But as you see here, still the encoding process is sequential. We cannot compute HT until we have computed HT-1. This makes parallelization during forward pass impossible, and for sequences it makes the training time very long, and for sequences of size hundreds or thousands of tokens, the training time will be very long. And this sequential process means that we are not really utilizing our GPUs, and the GPUs are mostly sitting idle, waiting for this sequential computation to complete. Why this is important? Because if you remember the CNN architectures, they are highly parallel. And that's why we could scale it to handle very large data sets. And that's what we want here also, to be able to scale the learning. That's not possible here. As for example, in the encoder, if we want to process, let's say 100 token sequentially, we need 100 serial steps. And if we want to generate 80 tokens in the decoder, we need 80 serial steps, which a total is 180 serial steps per training example, of course. You can think of parallelizing on the batch size, but a batch is of size, let's say 32, but our GPU has thousands of cores that will be vastly underutilized. So I mentioned that CNNs are great for, they are highly parallelizable, and they excel in image processing because nearby pixels are highly correlated. In other words, they have strong local correlation. But we know that text is different, and the most critical relationships can span long distances. So if we use a CNN, for example, for a sentence like the dog chased its tail, and if we want to use, let's say, local filters like this, and we know that eventually we can see all of this relationship like this, for an important relationship like dog and tail, we have to go up, let's say like this, to meet. And information must pass through many layers, and this degrades the signal, of course. And we want to come up with a different way of doing this encoding. So the idea that around 2017 was, well, we did the cross-attention, and we came up with this general attention formula that we discussed last time. So in this attention mechanism, we get the queries from the decoder or the query side. Keys and values came from the encoder or the memory bank. But of course, there's no requirement that Q, K, and V come from different places. They can come from the same sequence. For example, the sequence X that we want to encode, so the sequence is in R and D, and we can form queries and keys and values from the same sequence. What I mean is basically Q is X, W, Q, and each X is asking, what am I looking for in my neighbors? So X, for example, X2 here looks at all of the neighbors, and it's basically trying to see if there is a neighbor or neighbors that can improve its representation and add more context to it. Also, the same X provides keys. And here, key basically means what do I offer to others? And at the same time, value. What information do I contain? So each position in the sequence can attend to every other position to gather context. Let's try this in an example. So consider a sentence. Let's say the bank by the river offers great views of the boats. And let's look at the bank, position 2. And let's assume it acts like a query. What are my neighbors telling me about my meaning? It looks at the river, and the key of river is basically I'm related to water. Looks at offers, and the key is I might be a financial institution. And boats, which the key is, again, I'm related to water. And the model computes attention weights. And there's a high attention to river and boats and low attention to offers, let's say. And it combines these representations or values from these neighbors to basically add context to its meaning. So it realizes that, oh, this is a river bank, not a financial bank. And it's crucial to note that this all happens within the sentence itself. Each word refines its presentation by attending to related words. So that's how we update the embedding of each of these words or tokens, and we can encode them. And when we want to do the decoding in an autoregressive way, we're looking at the previous. So let's say we have a word here that we want to predict. We look at all previous words and query them to update it, the meaning of that or predict that. Note that during the training, we may have the future tokens also, which we have to mask to not let the model cheat by querying them. So this is called causal masking, which we will see in the code. Okay, so with that, let's go back to this scale.product attention and just review that one more time. And then using that, we can redesign this encoder-decoder architecture with self-attention and cross-attention fully. And we want to drop anything else that is, for example, related to RNN or CNN. So again, given a input sequence X, and this is in R, let's say n by d. Each sequence has n tokens, and each token has a d dimension. So this dimension here is important. Somehow tells us what is the dimension of the representation for each one of these tokens. And we call this D model. We will project them to this Q, K, and V spaces. So Q is XWQ, which projects X to this query space. Same for keys and values. So note that the Q space Q and K are in the same size because they want to look for their similarity, but the value space is not necessarily at the same dimension. So that's why we call it DV. That means that WQ and WK have similar dimension of D model by DK. WV has dimension of D model DV. And then we compute the attention scores using this scale.product, which is a square matrix. And entry I and J of this matrix measures how much position I should attend to position J. And then we applied the softmax. So if this is step 1, 2, 3, here we apply softmax to get attention weights, which is the same size, and each row sums to 1, giving a probability distribution over positions to attend to. And that basically let us do the weighted combination of all of these values, or the output that we are looking for, which is attention weights multiplied by V. So given that, what's the self-attention of X? It's basically softmax of the dot product of XWQ and XWK. Here we have a transpose, and then XWV. Okay, so let's look closely at this. Few observations. We don't care about the order. Everything attends to everything. So even if we shuffle the input, the output shuffles in the same way, right? So this is permutation equivariant. The entire computation is parallel, right? And all positions can compute their attention simultaneously. This is all-to-all connection. Every position can directly attend to every other position in one step. So none of those matrices, WQ, WK, and WV, depend on the sequence lengths. That means that the same WQ, WK, and WV works for any n, okay, which is very significant. Okay, so there are some nice computation aspects, right? But there is a problem here, and the problem is, where did the sequence order go? Previously, we had R and N, and order was inherent, right? Here, self-attention is basically a bag of vectors. For example, let's say, what's the output I? The attention output for position I, and that's basically the sum. And we know that sum doesn't care, it's just a weighted sum, and it's permutation invariant. So it's a bag of vectors, basically. We lost the notion of order. And that means that a sentence like, the cat chased the mouse, for self-attention is the same as the mouse chased the cat. That means that the self-attention basically produce identical representation for both sequences, but these sentences have opposite meanings. So we must explicitly provide positional information here. There are different ways of doing it, and we'll zoom into this positional encoding later. But for now, let's just say that the input to self-attention so far was token embedding, right? We have to update this with some positional encoding, and this will be the input for self-attention. So basically, positional encoding will be a vector of the same dimension as the token embedding, and it basically infuses the position to the embedding. But for now, let's assume we are not really learning this, and we can basically give this in a deterministic way. And given that, we know the relative position between words, and the encoder will consider that in the update of the embeddings. Okay, so with that, we know how to do self-attention. Now let's design our encoder-decoder architecture with this. So no more RNN. We want to do everything with attention. So self-attention within the sequence and cross-attention between the encoded and decoded sequences. Okay, so let's rewrite this. We have the input X, here the embedding of X, and then we are adding the positional encoding, and now this is the new representation for each tokens. So now we want to do self-attention. From the same X, here, let's call this X, we have Q, K, and V. So each sequence attends to itself. Okay? And then, like we discussed before in the previous lecture, we need some form of nonlinearity. So the nonlinearity basically helps us to get these rich functions that allow for these linear spaces to work. We need a feed-forward neural network. That's the output of this attention layer. This is one attention layer. So we can, of course, repeat and stack several of these layers, stacking n times of them. And at the end, we will have keys and value pairs. That is the output of this encoder. Okay. So now we want to use this to decode or generate new sentences or sequences. Let's just repeat the same thing. Just copy this. So now the output follow the same thing. Here we have output embedding, and again positional encoding, and then again self-attention within this decoder sequence. But we want this decoder to talk to the encoder state, right? So before sending it to the feed-forward neural network, we will add another attention, but this time across attention. Like what we did before, we allowed this decoder sequence to query the encoder. So like I said, this is basically a cross attention. And then the output of this guy goes to the feed-forward neural network. And that's basically a decoder attention layer. And we can have another bunch of these layers stacking on each other, okay? And then we can send this updated representation to, let's say, a linear neural network and a softmax. So the linear gives us the logits, the softmax gives us the probabilities, and this basically is the output probabilities, which we sample from, and we get the next token, and we repeat this, okay? And that's the autoregression way of decoding. There are, of course, some architectural trick to make this stable and make sure it's learning. For example, if we want to stick with the original paper by Vaswani et al., they added skip connection to all of these blocks to make sure we have this residual highways, and then a form of normalization that makes sure the variance is controlled. So let's add the skip connections. We have one here and one here. Same on the other side. And as you remember in CNN, it's always good to do normalization to make sure things are scaled and there is no covariance shifts, for example. And to do that here, we're using layer normalization. And to do that here, the original transformer paper proposed layer normalization in this form that I'm going to write here. So here is the normalization, and as you see, it basically makes sure the signal that we are sending upward is always stable and scaled. And of course, the skip connections or the residual are making our gradients reachable to the deeper states. Okay, so let's again review. We have this input embedding. We add the positional encoding. We have this encoder self-attention, which each position attends to all positions in the input. And then we have the decoder, which is masked self-attention, meaning that each position attends only to previous positions. This is the causal masking that I mentioned. Of course, we have this cross attention, where the decoder attends to encoder outputs, same as last lecture. We have these feed-forward neural networks that provides this expressiveness that we want. It also acts like a learned feature map that we discussed in the kernel discussion from last time. Most of the parameters are in this feed-forward neural networks. So looking at them, and it's good to zoom in into this sublayers and discuss the importance of them and why they are carrying the most number of parameters, and we expect them to carry most of the expressiveness of the neural network. So basically the self-attention part, it mixes the content, and fit for a neural network provides these nonlinear transformations. And why they provide this kind of separation of concern for us. So let's think of these transformers like a librarian. I mean, after all, large language models are following these transformer architectures. And somehow we have this impression that they are memorizing the internet. Of course, it's a lossy compression, but it's a very, very efficient compression. And that's why let's make this analogy. And it's like we can think of transformers like a librarian that reads and summarizes and organizes the library. And it comes up with this efficient shelving, basically the embedding space. It organizes these summaries by placing similar concepts next to each other. So again, this organizational system is the model's high-dimensional vector space that it learns via this gradient descent. And then there is a knowledge store, which, like I said, requires the most number of parameters. And that's mostly carried by the feed-forward neural networks. So you can think of these feed-forward neural networks like memory also. So they are like the specialized bookshelves where the compressed knowledge is stored. When we provide a prompt or a query, we're asking this librarian a question, and the attention mechanism acts like an efficient search that allows the librarian to instantly identify the relevant sections because the library is organized by similarity, and compares the query or the request against the keys or the indices, let's say, to find relevant concepts. So attention decides where to look. And once the attention gathered the relevant context, the feed-forward neural networks accessing the specific knowledge or the values associated with the context to determine the next word, for example, here in LLMs. So the FFNs or the feed-forward neural networks decides what information to apply. So we can think of it like attention is basically performing content-based routing or mixing across all tokens, which is like the librarian is finding the right aisles. And feed-forward neural networks perform this token local computation that acts like a dense associative memory, which is like the content on the shelves. So even if you look at an FFN, so let's write it like this. A two-layer FFN is like this, right? So looking at this component-wise, let's assume ReLU. We can rewrite this in a summation form. J throw F. So let's look at the one row of this computation. So 1J, which is J throw of W, W1 plus B1J. So this is a ReLU. It means that when it's negative, it gives 0. So this is only positive or 0. Multiply by Vj. So Vj is the jth column of W2. So let me write this down. Jth column W2. And this is jth row of W1. So let's zoom into this. This part is basically deciding if the neuron is activated or not. Corresponds to the first layer, right? If it is activated, a value Vj will be written to the token string, which corresponds to the W2. So you can think of it like this is like a key and this is like a value, right? Just like what we did previously with kernel regression. So you can think of a dense feed-forward neural network as a large bank of key and value pairs softly selected by an input context X. In other words, it's like really like a mixture of expert, where an expert is invoked and the opinion will be seeked. So during the training, these W1Js push to activate a specific contextual patterns. And the VJs, or the values, point toward directions that raise the correct next token logits. So we can think of this pairs of W1, J, and VJs as storing the association for context and next token. Many such pairs superpose and yielding a sparse distributed memory. Remember that this also does interpolation between what it observes in the data. So the interpolation comes from the fact that this gate here varies smoothly with X. In mathematical language, we basically say ReLU is Lipschitz, and this makes nearby context activating similar neurons. So it's like a piecewise linear kernel smoother, really. Great, so that's the interplay between the attention and the feed-forward neural networks. Here, the last point before moving on, when we look at the attention head, it basically computes the output as a weighted average of the value vectors across all positions. This averaging mechanism can dilute information and somehow prevent the models to focus sharply on different aspects of the sequence at the same time. For example, in language, we have different relationships, like, for example, semantic roles and positional context and so on. And if we want to compress all of them into one weighted sum, it reduces the effective resolution. So to counteract this reduction in resolution, we use multiple attention head. So we have several of them. And looking at the figure 2 of the original paper, here, for example, we have H attention head. Each attention head gets a subset of the embedding space, right? So for example, if the embedding space is dV, we chop it into H, and each attention head attends to one of the representation subspace. So at the end, all of these outputs of these attention heads will be concatenated to obtain the updated QKNV. We can discuss the details of positional encoding and the normalization. Let's discuss the positional encoding in transformers. And first, we list a bunch of properties that we like an positional encoding scheme to satisfy. We like each position to have a distinct representation, so a uniqueness property. Ideally, we want the encoding to be reproducible and not random, so determinism. We want this to have a bounded range. We don't want to mess up with the embedding that we are updating during the transformer layers. So bounded range. And it should work for sequences longer than those we see during training. So generalizable. The encoding must distinguish between near and far positions at different scales, right? So somehow a multi-scale distance awareness. We don't want to mess up with the continuity for gradient descent, so the nearby positions should have similar encoding, so some kind of smooth transition. Also, since we are dealing with linear transformation in the embedding space, any shifting position, let's say from I to I plus delta, should correspond to a simple linear transformation, for example, a rotation. So linear transformability. Okay, so let's start from the simplest ideas and build toward a scheme that satisfies all of these properties. So let's assume a sequence of size of length n. One simple encoding is to basically assign each position a normalized scalar value between 0 and 1, right? So basically from 0 to 1. So the positional encoding will take a form like this. And then we can update the embedding of input, let's say at position I, with EI plus PI. And since we want this to be a vector of size d dimension, this should be a one vector, okay, which is in d dimension. Okay, so let's look at this simple encoding. So one issue here is this linear transformability. If you look at this, all of these encodings are these parallel vectors of direction one. So they are all point in the same direction and they only differ in magnitude. So if you write the score between, let's say, EI and EJ, this will be like adding the same global bias to everything. In other words, if you have, let's say, a two-dimensional embedding, let's say the embedding of cat is here, the embedding of sat is here, the embedding of mat is here. This positional encoding will add just a vector like that. And there's not really a distinguishing geometric structure. So what we can learn from here? First, we need a multidimensional structure. This is not multidimensional. We need a rich geometric interaction. So we need some form of meaningful geometric relationship after these updates. And we need some form of directional diversity. So different positions should point in different direction, not the same direction. So let's do another attempt. And for that, we will bring from our previous knowledge, and we want to represent each position using this binary coding. So again, this is the axis of position, let's say 0 to, I don't know, like 0 to 7. And we want to represent this with different beats, right? For example, so we can go on and on, but basically the idea here is we have the finest scale here, we have a medium scale here, and we have a coarse scale here with different periods. So this looks much better. Each bit provides a different level of positional information. We can distinguish nearby positions. We can also distinguish distant position. So previously, if you remember, previously it was easy to distinguish distant relation, but not nearby relation, okay? But here, that's not the case. We can basically compare nearby relationships with the higher frequency and the distant relationships with lower frequency. So this works in terms of being multi-scale. Different dimension captures different granularities of position. It is unique. It allows for easy distinguishing between local, let's say here, for example, 1 and 2, and global 1 and 7 by using different periods and different scales. However, the main issue here is it's not smooth, and we want to deal with continuous functions, and sharp discontinuities makes our optimization very difficult. So let's make it smooth. Instead of bits, we'll work with waves. And the natural choice here for these oscillating functions are sine and cosine waves. Okay, so basically, instead of this, we have like slow period or faster period or an even faster periods. These are bounded, but the nicest thing about this sine and cosine pairs is it is compatible with rotation. And that rotation is naturally expressed using sine and cosine. For example, rotation in 2D with theta angle can be written like this. That's a rotation. And in the case of positional encoding using this sine and cosine, the positional encoding between two words, like word 1 and word 2, with a distance delta corresponds to a rotation of delta. Now, of course, the choice of the frequency depends on the length of this dimension. Okay, so with this, let's build the complete formula. So for position I and dimension j, we are asking for a sine or a cosine. So depending if it's an odd dimension or an even dimension, so let's say 2j or 2j plus 1. The formula for this guy is a sinus of I, position I, but with these frequencies. For the odd position, we have cosine of I, same frequency. So if we want to plot this, this is basically like faster frequencies. When you go down, you have slower frequencies. Again, it's easy to distinguish between long distances and small distances using this balance of scales. And these pairs of sine and cosine help us to interpret this distances like rotation in this embedding space. So if you look at each position, so looking at this will look like something like this. And if we want to relate this to this very common figure, it's basically faster frequencies here, and then slowing down. Here, for example, this is just a depth like this, and slower, okay? So this is the default, this is the first positional encoding that was proposed by the original transformer paper, but there are many other positional encodings. There are even learnable positional encodings that can be useful for some specific applications, let's say like time series analysis. And I encourage you to play with different types of positional encoding